wouldn't be uncomfortable at all if somebody walked in and was just napping in the corner. All right, let's take a look at this. So this is reviewing all the probability stuff from chapters 5 and 6. So suppose you and a friend are playing a game where 2 dice are rolled. If you roll a 5 or a 9, so a sum of 5 or sum of 9 on the first roll, you win. If you roll 4, 6, or 8 on the first roll, you lose. I think way back when, like in our chapter 5 notes, I did give you a diagram of like if you roll 2 dice, all the possible outcomes. So you're welcome to pull that out to look at it if that helps you, if you have trouble like visualizing those. On the test, if I were to ask you something about like rolling 2 dice, I would probably give you a diagram showing you all the outcomes just so you can kind of keep track of what you have. So we want the sample space for winning and losing. So sample space is just listing all the possible outcomes. So different ways you win. I'm going to write them as like an ordered pair. You don't necessarily have to. But if I want a 5, how could I get a 5?
2, 3.
We could roll a 2 and a 3. Can we also flip the order? Because if I'm thinking like, if I'm rolling my special one, I've got my green dice and a white one. Okay, is it different to have the 2 on the green and the 3 on the white versus 2 on the white and the 3 on the green? Yeah, so we can flip the order. We have a 1 and a 4, 4 and 1, and 4 and 1.
So we really should be a few of us that went
Okay, so those are how I can get a 5. We could also win by getting a 9. So how can we get 9? 6 and 3, or 3 and 6, 4 and 5, 5 and 4. Okay, so that's my sample space for winning. How do we lose?
Roll 2, 2.
Okay, we can lose with a 4, so 2 and 2. With, can I flip the order on that one? No. Because we already have 2s on both dice. We could get a 1 and 3, 3 and 1, so that's every way to get a 4. To get a 6, we could do 1 and 5, 5 and 1, 2 and 4, 4 and 2, or
3.
3 and 3. And to get 8, yeah, we have a lot of these. We could have 2 and 6, 6 and 2, 3 and 5, 5 and 3, 4 and 4. So those are my sample spaces. If you had that diagram, like with a list of all the outcomes, you guys feel like you could come up with this list?
Yeah.
Okay. So find the probability you win on your first roll. So from that diagram, or if we think about it when I roll, there's 6 options for the first, 6 for the second. 6 times 6 gives us 36 total outcomes. How many of them are winning? 8. So 8 out of 36 is 2, 2, 2, 2. All right, part C, find the probability you lose on the first roll. So how many total outcomes do we have still? 36. How many of them are losing? 13. So 13 out of 36. 3, 6, 1. Is that one okay?
How did you get to 36 again?
36. So I thought about when you roll the first dice, there's 6 options, and the second one, there's 6 options. So 6 times 6. Okay. Let's do one from a table. So I have given you the probability distribution. How do we check if it's an actual probability model?
Have to add up to 1.
Okay, so check if we add these. We get 1. So it is a probability model because it adds to 1.
And it's between 0 and 1.
Yes. And every probability is between 0 and 1. Because we know we can't have a negative probability, we can't have a probability higher than 1. So if I'm checking if something's probability model, we are listing all those probabilities. Every one of them has to be a number between 0 and 1. And it has to add up to 1. All right, B. What's the probability a person travels in a car? So if I look, I'm trying to figure out which of these are in a car. So carpool would be in a car. Would any others?
Drive along.
And drive alone. We're assuming you're going to drive a car to work, not a bus or something like that. So, what do I have to do with those then?
Add.
So we get 0.875. C says, what's the probability a person drives alone? So here's my drives alone with someone. Okay, so with someone would be carpooling. Or on public transportation. So I'm just asking you to add those 3 numbers. We get 925. And part C, what's the probability that someone does not walk?
1 minus.
So you have 2 options. You can go through and add up everything that's not walking, so driving alone, carpooling, public transportation, other means, or working from home. Those are all not walking. Or the easier option would be, well, not walking is just the opposite of walking. So 1 minus 0.025. We get 0.975. Even if you just added all those other ones up, you'll get the same thing. Questions on that one? Number 3. Suppose a hitter reaches base 30% of the time he comes to the plate. Part A. What's the probability he reaches base 3 times in a row? Okay. Does the probability change the second time if you made it the first time? No, I'm just saying straight 30% of the time we make it. So the first time, and the second time, and the third time we make it. So what do we have to do?
To 30.
Yep. You just have to multiply it 3 times or say to the 3rd power. Either way it's the same. Because we know and is multiply. So this time, and this time, and this time, we're just multiplying those. And we get 0.027. What's the probability he will not make it to base in at least one of the next 10 at-bats? So here, there's a lot of possibilities. I'm saying at least once he doesn't make it in the next 10 times. So it could be he didn't make it the first, or the second, or the third, or the fourth, all the way up to the 10th. It could be he didn't make it 2 of those times, or 3 of those times. That's a lot of calculations. What's the easier option? Complement. Not making it at least once. Isn't that the opposite of making it every time? So complement is 1 minus. What would, to find the probability he made it 10 times, that would be my 30% to the 10th power. So we're doing everything except the possibility that he makes it every single time. I get point. Okay. So extremely likely one of the next 10 times he is not going to make it. So this was just using that independence. If those probabilities are independent, all we have to do is multiply them together. Number 4. A committee of 4 women and 3 men will select 2 people to attend a conference. What is the probability that 2 women are selected? So we have 4 women and 3 men. I want 2 women, so I need the first one to be a woman and the second one to be a woman. And means what? Multiply. So we are going to do multiply. So the probability that the first one is a woman. So I look, I have 4 women to choose from out of 7 total candidates. But if I have now selected one of those women, the next time I go to pick a person, how many women remain? 3 out of how many people? 6. That probability for the second one changes because I already took one of the women out. Did give us a total column here. So, the World Factbook in 2008 reported that U.S. airports have the following number of meters of runways that are either paved or unpaved. We are finding all the probabilities. So the probability of paved. How many are paved? What am I going to divide that by? Yes, we need to add both of those to figure out my grand total. $14,951. So if we divide those, all right. B. 914 to 2,437 meters of runway. So I didn't specify paved or unpaved, so it's all of them that are anywhere between 914 and 2437. So that would be those 4 numbers. Add those together. part C. This time it says less than 1,524 meters and unpaved. So less than 1,524 means it could be one of these two groups, but it has to be unpaved. So I'm only looking at those two. Those are the only ones less than this length and unpaved. So we get 0.64497, so it's 0.645. Are we doing okay so far? The next one, more than 2,437. So more than 2,437 is the first two categories. And paved. So over that and paved, just be those two numbers. $417. Zero two seven nine. All right. Now E. These are givens. When you see a given, that means it is no longer out of everything. My condition is it's more than 1,523 meters of runway. So on my table, I'm only looking at things that are more than 1,523. So that's these 6 numbers. That's all we're looking at. So that's my total. We have to add those up. And that would be our denominator. Of those, we want the ones that are paved. So I'm only looking at those 6 highlighted numbers so far, but I want the paved. So there's 3 numbers I have to add up. That's 1,881. Divide, we get 0.9207. So the givens are when we are not looking at everything. We just have a portion. F. Less than 1,525 meters of runway, given it is unpaved. So my condition is unpaved. That means in this, I am only looking at my unpaved. Okay, so we can basically cover up the other half of the table. So my total is just the unpaved ones, which we did already have added up for us, the 9805. The numerator, we want the ones that are less than 1524. So I'm only looking at what I've already highlighted. Less than 1524 would be these two numbers. So we get
Okay, thanks.
And we get 0.9835. Alright, last one. Unpaved, knowing, that's the same thing as given, it has less than 1524 meters of runway. So, I already know it's less than 1524. So if we're looking at all the numbers, less than 1524. So that's those four numbers. And that will be our denominator. Okay, the numerator, we want those that are unpaved out of that group. So I'm only looking at my highlighted numbers, my unpaved ones. You're welcome. See you later. Yeah, probably. So we get 9643. So that's 0.747. Any questions on those comments? So the thing to watch, if it is a given, that changes the denominator. And so that's the only thing I'm looking at. So cover up the rest of the table or something so you're not adding in unknown or unneeded numbers. Alright. Next one. I apologize, I think the numbering was off on your copies. I fixed it when I made my slides, but it should be number 6. Determine if each variable is discrete or continuous and give the possible values. So this is our more recent stuff. The number of saved telephone numbers on your cell phone. Would that be discrete or continuous? Discrete. Okay, possible values. Can it be a negative number? Can it be 0?
Yes. Oh.
Yeah, it could be that you haven't saved any numbers, and then it's only countable. So 0, 1, 2, 3. Is there a maximum here?
No.
All right. B, the weight of a statistics textbook. Discrete or continuous? Okay. Can it be negative? Can it equal 0? No. So it just has to be x is greater than 0. And then could it be any decimal value there? Here's 7. In a game of roulette, a player can place a $5 bet on the number 17 and have a 1 in 38 chance of winning. If the ball lands on 17, the player wins $15. If not, the casino keeps the $5. What is the expected value to the player? All right. So I am talking about expected value. If you go to your formula sheet, chapter 6, the very first bullet, what does it say?
Some of the means
Says mean and then in parentheses expected value. So I'm asking you to find your expected value, which is your mean, and tells us the mean is the sum of x times p of x. So let's make a table for x and p of x. Okay, we are talking about money here. So x is going to be like our dollars. $5 bet. So what happens if you lose?
$5.
Okay, you lose $5. What is the probability that we lose?
0.97. It's 37.
Yeah, if there's a 1 in 38 chance of winning, then there's a 37 in 38 chance of losing. If you type that in, it's a big decimal. Let's try not to round too much too soon. So I'm just going to keep it as 37 out of 38 for now. Not that it would necessarily be wrong to go ahead and divide it, but I don't want more rounding error. Okay, so either you lose or you win. If you win, you get $15. But did you really make $15? You only made 10 because you paid them $5 to play. They give you 15 back. 5 of it was yours. There's only a 1 in 38 chance of this happening. So we need to find the x times p of x. So -5 times 37 out of 38 gives me -4.684. 10 times 1 and 38. Gives us 0.2632. So then what do we have to do to those? Add them together. So we get -4.6052, or we're talking about money. So we have an expected value of -4.61. In other words, if you play 10 times, you would expect to lose $4.61 on average for every time that you played. So it's not beneficial. If you were thinking about gambling, the odds are not in your favor. Okay, you're going to lose. Don't do it.
I'm very good at gambling.
Any questions on that one?
I think a scratch off ticket's the only thing that are really good. I think I'm really good at horses.
Yeah, you can get
Gambling is bad.
Yeah,
Don't
but
do it.
it's just all a scratch off ticket. It's just all a scratch
off
off ticket until it's 50. No, that's I get stuck. I won $20. I put all $20 back into the scratch offs and I lost.
Yes.
Like
Yes, they are
Addiction
rigged against
runs
you.
in my family and I just
Don't
can't.
do it. All right, number 8. Consider this function. Form a probability distribution table, including x times p of x and x squared p of x. So the probability distribution is just your x and your probability. But we did those other columns when we were finding like mean and standard deviation by hand, so I went ahead and told you to put them in here to practice. Okay, I didn't give you the probability of these things, I gave you the frequency. So if we add them up, how many total do we have? 100. So to get your probability, you take your frequency divided by 100. So 10 divided by 100 is 0.1. When x is 1, 50 divided by 100 is 0.5. When x is 2, 5 out of 100 is 0.05. 3, 25 over 100, 0.25. And at 4, 10 over 100 is 0.1. And if you check, does that add up to a probability of 1?
Mm-hmm.
Yes, so we know we're on the right track. Okay, from here, we're just doing what the formula says. X times p of x. So 0 times 0.1 is 0. 1 times 0.5. 0.5. 2 times 0.05 is 0.1. 3 times 0.25, 0.75. And 4 times 0.1 is 0.4. The final column, x squared p of x. So it's 0 squared times 0.1. 1 squared is 1 times 0.5. 2 squared is 4 times 0.05. 0.2. Do you guys know where I'm getting these numbers? Okay. 3 squared is 9 times 0.25. 22.25. 4 squared is 16 times 0.1. 1.6. So we made the probability distribution, we added in the extras because I asked for them. Okay, graph the probability distribution. That's where we just list each x and its probability. So 0. Okay. I'm going to count by 0.1. So then we can just draw a line up to our probability. So 0 was 0.1, 1 is 0.5, 2.05, 3 is 2.5, and 4 is 0.1. Sometimes I ask you to describe the shape. I didn't here. If you had to, how would you describe it?
Skewed right.
Skewed right. We have more points to the right here. Okay, find the mean. If you don't remember, look at your formula sheet. If we're talking about a probability distribution, that's the mean or the expected value. It's just the sum of the x times p of x. Okay, we already did that column up here. So we just have to add up all of those numbers, and we get just to show you what I'm doing, I'm just adding up that column. D, find the standard deviation. So if we look on our formula sheet, it tells us for a probability distribution, it's the square root of the sum of the x squared p of x's minus the mean squared. So I have to add up my x squared p of x's. Add all those. Minus I don't know why I wrote mean sub 2. I said squared, didn't I?
Yeah.
I just wrote it as a subscript. Minus 1.75 squared. So I'm just going to type that all in my calculator. Is that okay? Last thing I asked for was variance, which if you're looking at your formula sheet, it doesn't have it right there, but we talked about variance back at the beginning in chapter 3. It's just the standard deviation squared. So variance, we just take what we got for our standard deviation and square that. And get 1.4874. There is a potential, like if you hadn't rounded this number, you might have gotten 1.4875. So just make sure you're showing me what numbers you're squaring, because rounding does change a little bit on here. All right, is that one okay? So let's get into last part. So this is our more recent stuff, the binomial, like we were doing yesterday. This one says to calculate. So if I'm asking you to calculate it, that means by hand, or not really by hand, but using the formula. So remember, our formula is n choose x, p to the x, 1 minus p, so 1 minus 0.3 is 0.7, to the n minus x, 4 minus 1 is 3. So we did that on our calculator. 4 choose 1, 0.3 to the first, 0.7 to the third, we get 0.4116. B, n choose x, so 2 choose 0. P, 1/4 to the x, to the 0. 1 minus p, so 1 minus 1/4 is 3/4. To the n minus x, 2 minus 0 is 2. If I tell you to do it by hand, then make sure you are writing out your formula so I know that you did it by hand. I'm probably more likely on the test just to give you one that you couldn't look up on the table if I want you to do it by hand, because we know there are some that aren't on there. And so we get 0.5625. Then I asked for you to do some using the table. So let's double check if we can do that. So on number 10, my n is 15. So I go to my back page when n is 15. X is 3. P is 0.05. What is our number?
0.0307.
B, n is 8, so we have to go back a page. X is 7. P is 0.95. And we get
0.2713.
Did everyone find those on their table? A few more questions, see if we can get through them. In a binomial distribution, n is 11 and p is 0.05. Find the mean and standard deviation. So if we look on our formula sheet, back in chapter 6, it tells us in a binomial distribution, so it's the second column, the first one, the mean is just n times p. So 11 times 0.05 gives us 0.55. Standard deviation is the square root of n times p times 1 minus p. Square root of 11 times 0.05 times 0.95. .7228. Are those okay? This question is actually kind of from the very beginning, empirical versus classical. Empirical is, so the difference is what we would expect to happen versus what does happen. So when we look at this, what we actually observe, so we roll a die 5 times, we get a 1 twice. Probability of 1 is 2/5. I don't remember if this was on your formula sheet.
It is. It's the beginning of chapter 5.
So if we look back to the beginning of chapter 5, you can kind of see empirical is just how many times it happened divided by the number of trials. Classical is more like what we would expect. How many times could it happen? If I'm looking at this, I observed it twice, so I put a 2 on top. There are 5 different options, so 2 out of 5. So it's what we saw out of the total. So which one is that? Empirical. Okay. This one, the number 1 is expected to appear 16.67% of the time. That's because 1 divided by 6 is 16.67. There's one number 1 on the dice out of 6 total sides. So that's based on how many times it could happen out of the number of possible outcomes. So that is classical. All right, and if you forget which is which, looking at that formula sheet can help you there. All right.